Problem number 1. Compute the design moment strength of the beam shown if Fy is equal to 420 MPa and F prime C is equal to 21 MPa. Check the maximum permissible AS to ensure ductile failure. ES is equal to 200,000 MPa. So, able to solve the problem number 1, so let us determine first the given. So this is the figure of problem number 1, in which we can see that it has three steel bars with 29 diameter and 4 steel bars with 36 diameter. Given the dimensions, we have our B is equal to 450 and our D is equal to 650 and our D prime is equal to 70 mm, and this dimension 580 mm is equal to D minus D prime. We also have our Fy is equal to 420, Fc is equal to 21 MPa, and Es is equal to 200,000 MPa. So for the first solution, let's determine first the area of the steel, which we can see in our figure before. So the first is with 36 diameter and it has a 4 equal bars. So first is 8s is equal to 1/4 pi times 36, the diameter of the bar, squared times 4, we can get 4071.50 mm squared. So the second one is with 29 diameter, which has a 3 equal bars, and then we can get a 1/4 pi times 29 squared times 3 is equal to 1981.56 mm squared. To begin the solution for the design moment strength, we have to get first our A, because A involves in our formula right after this. So A is equal to AS minus A prime S times Fs over 0.85 times F prime C times B. So we can get an equal of 4071.50 minus 1981.56 times 420 divided by 0.85 times 21 times 450. So the result is A is equal to 109.28, and additional information, if we can get D minus D prime is equal to 580, considering our figure before. To continue the solution, we have to get our moment, which is our moment is equal to 0.85 times F prime C times A times B times D minus A over 2 plus S prime S times F prime C times D minus D prime. We can get 0.85 times 21 times 109.28 times 450 times 650 minus 109.28 divided by 2 plus 1981.56 times 21 times 580. The resulting value is 546.74 kilonewton meter. So we have also to get the maximum strength of the beam. So 0.9 times 546.74, which is our moment, whereas in this formula we only get it that 0.9, that our phi is equal to 0.9. So our maximum moment strength of the beam is equal to 492.07 kilonewton meter. The next thing that we need to do is to check the maximum permissible area in order to ensure ductile failure. And with this formula, we can use it to determine if we can ensure the ductile failure. So AS is equal to AS plus A prime S is equal to 4071.50 plus 1,981.56, resulting 6,053.06 mm squared.
Ara good.
P equals to A S over BD, equal to 6,053.06 over 450 times 650, we can get 0.0207. So our P prime is equal to S over prime divided by B times D equals to 1,981.56 divided by 1,450 times 650 equals to 6.77 times 10 to the power of -3. To continue the solution, we have to get the ratio of the stress of the concrete is equal to 0.85 times beta 1 times F prime C times D1 divided by our Fy times D times our modulus of elasticity over modulus of elasticity minus the modulus of elasticity in the bottom part plus our ratio prime or P prime rho prime equals to 0.15 times 0.85 times 21 times 70 times 420 times 650 times 0.03 times 0.003 minus 0.021 plus 6.77 times 10 negative 3. Since our FC is equal to 21 MPa, which is less than 30 MPa, so our beta 1 must be automatically 0.85. So we can get a resulting value of 0.0197, which is our rho CY times rho is rho CY is less than times our rho. So from determining the value, which is our rho CY is equal to 0.0197 and our rho is equal to 0.0207. So therefore, we can ensure the ductile failure. So the problem number 2 is a rectangular beam reinforced for tension at the bottom. Area of steel is equal to 5,087 mm squared, and at the top, area of steel is equal to 2,035 mm squared, with the width of the beam is 280 mm and a total depth of 590 mm. Steel covering at the bottom is 80 mm and at the top is only 50 mm. If F prime C is equal to 35 MPa, Fy is equals to 400 MPa, assume all steel yields. First is, letter A is to determine the location of the neutral axis from the top of the beam. Letter B is to determine the value of compressive force carried by concrete alone. And letter C is to determine the ultimate capacity of the beam. So the first solution is the solution for determining the location of the neutral axis, which our referring formula is equal to C is equal to A over beta 1. So we have to get A first in order to use this formula. So A is equal to AS minus A prime S times Fy times beta 1 divided by beta 1 times F prime C times D is equal to 5,087 minus 2,035 divided by 0.85 times 35 times 280. So A is equal to 146.55. From determining our neutral axis, beta 1 is also included in the formula. So we need to get it first. So since our F prime C is equal to 35 MPa, which is greater than 28 MPa, therefore we need to use this formula, which is beta 1 is equal to 0.85 minus 0.008 times F prime C minus 30 equals to 0.85 minus 0.008 times 35 minus 30 is equal to 0.81. So we can say that NA, or the neutral axis, then is equal to C is equal to A divided by beta 1 is equal to 146.55 divided by 0.81. We can get a value of 180.93 mm. Letter B is to determine the compressive force of concrete alone, or CC, denoted as CC. C sub C. So C sub C is equal to 0.85 times F prime C times A times C is equal to 0.85. Our F prime C is 35 Newton millimeter squared times 146.55 times 280. So we can get a resulting value of 1.22 kilonewton. The last part that we need to identify is the ultimate moment capacity, or denoted as MU. MU is equal to moment capacity of 1 and plus moment capacity of 2. Area 1 and area 2 is equal to A prime S times Fy times D minus D prime plus AS minus A prime S times Fy times D minus 9 over 2 equals to 2035 times 400 times 540 minus 80 minus 50 plus 5067 minus 2085 times 400 times 50 minus 146.55 divided by 2. And we can get a resulting value, or our ultimate moment capacity is equal to 907.59 kilonewton meter.